So let's dive into the Mastercam file that created this part and kind of talk about some of the specifics about how we were able to achieve this surface finish in Mastercam. So on my screen here, you can see we're looking at the actual finished part with the 3 different depths of the embossing. So the green, red, and purple surfaces represent 5, 4, and 3 micron tall embossed surfaces. If I turn these off, we see the actual base surface. So really, this whole part was programmed off of that single, very simple base solid. This is a compound curve, so you can see it's curved in both directions with variable radii. So really it's 2 splines that are swept together. And this is the actual surface we use to drive all of our finished toolpaths as well. Looking at the first toolpath, Op1 is just a traditional vertical 3-axis roughing toolpath. This is an area roughing toolpath where we used a NS Tool 6mm carbide ball. This toolpath ran in under an hour. It was about 45 minutes or so to rough the entire part. Of course, roughing the part like this, we end up leaving those stair steps from our roughing toolpath, which is where we come in with a semi-finished toolpath. So the semi-finished toolpath used the same cutter, 6mm tool from NS Tool. However, this toolpath is a multi-axis toolpath. So you can kind of see as the passes are going to run lengthwise across this part, and as the tool progresses along up this face, we actually increase the side tilt. The advantage of this is we're actually spreading the load of that cutter across a larger area of the functional area of the tool, increasing tool life. This toolpath also ran for about an hour. Pretty much default tolerances on this one because we're just getting the part to a little bit closer to the net shape. We're just really getting rid of those tall stair steps. The important thing to know in this case is that we're leaving 0.04 millimeters of stock, so 40 micron of material are being left on the part right now. And this has a pretty healthy step over of 0.15 millimeters. Now, after that, we run a deburr toolpath. That just kind of knocks off any burrs from the roughing process. And then we get into the really cool, interesting stuff. So from here, we have 2 special cutters from NS Tool. The first one is a CBN ball end mill. This is also a 6mm tool. What the CBN does is essentially gets the part basically right to size. It leaves a really nice surface finish. In some cases, this is already a good enough surface finish for most people. This is leaving 4 micron of material for the finish tool. That is hardly anything. It's just barely leaving a little bit of dust left. Cut tolerance on this toolpath is 1 micron. Now, tolerance is where this whole thing is done, really, where we really need to make lots and lots of points to create as smooth of a flow of points across this part as we can. The more points we have, the more data we're giving the machine, the more control we have how that machine is being moved. We know that Yazda is going to move exactly where we tell it to, and it's going to do everything to perfection. So the code from Mastercam needs to be perfect before we put it inside that Yazda. The finished toolpath is really where everything is done. And one thing you might notice, we're using a unified morph toolpath. The morph is kind of an old school toolpath in Mastercam as far as multi-axis goes. We now have guide and automatic cut patterns. The advantage of using morph in this case is I have access to a chaining tolerance. Chaining tolerance and toolpath tolerance are 2 different things. So toolpath tolerance, right here, we have a 20 nanometer toolpath tolerance. This thing is making tons of points, and that toolpath tolerance has everything to do with how deep, with respect to that surface, the cutter is going to be. This thing is going to be within 20 nanometers of perfect on that surface. But the chaining tolerance is actually of equal importance when it comes to surface finishing. So chaining tolerance is responsible for creating the actual morph between one edge of the part and the other. Now, you think this part's just a flat on both sides, but because it's a compound curve, that chaining tolerance becomes extremely important. So let's take a look at another part I have prepared here, just to show the importance of chaining tolerance. So here we see 3 different toolpaths with 3 different chaining tolerances. It's the same tool, the same cut tolerance. The only variable is chaining tolerance. So we're running a morph toolpath, just like with the surface finish part here. First, we see a 0.5 millimeter chaining tolerance. This is above the default. The default is 0.1. So we can see how the point spread changes from one to the other. The points seem really sporadic on the 0.5 millimeter chaining tolerance. Go to a 0.1, they really tighten up quite a bit. And then stepping down to the 0.01 chaining tolerance, that flow of points is much more under control. Changing your chaining tolerance is a really fascinating way of controlling that point spread. Cut tolerance is extremely important when it comes to controlling the depth of your cutter with respect to that surface. Chaining tolerance does the rest. That is what creates your point spread, and it's extremely important to be aware of chaining tolerance when you want to create a really nice surface finish. So going back into this part, we can see this tool, this PCD ball end mill, is only taking off 4 micron. It's running with an insanely tight tolerance with a 9 micron step over. So this finishing toolpath with the PCD ball took about 45 hours to run. This entire part was done in just under 60 hours. So this is a really big part, a really big commitment. So Mastercam, NS Tool, Methods, Yazda all came together to produce this beautiful showpiece. Now, in the next video, we're going to talk about quantifying just how great this part really is. We're going to learn about some surface finish measurement techniques and how they were applied to this part.